So this we can continue. So if we represent a complex function as gx plus jgy, then del gx by del sigma by Cauchy-Riemann condition is satisfied by saying that del gx by del sigma is equal to del gy by del w, del omega, and del gy by del sigma is equal to minus del gx by del d omega. So let us take an example. Suppose gs is 1 upon s plus 1. So you can write this in terms of replace s by sigma plus j omega and write it in terms of jx plus gjy. So it is basically 1 upon sigma plus j omega plus 1, right? And if you want to separate the real and complex part, then what we do, we multiply numerator and denominator by complex conjugate, right? This is how we separate the real and imaginary parts. So in this gj omega, we multiply complex conjugate of this on the numerator and denominator side. So what is complex conjugate of sigma plus j omega plus 1? Anybody in the class?
Sigma minus j omega
Plus 1.
plus 1.
Right. So substitute it, multiply it on the both numerator and denominator side. You will get the real part like this. Okay, and imaginary part like this. You do it yourself and you verify this result. Right? You are getting it? You have to apply that formula a plus b into a minus b. What is a plus b into a minus b? Substitute that, you will get gx like this and gy like this. Now from this, you can see that except at s equal to minus 1, gs satisfies the Cauchy-Riemann condition. That is what is Cauchy-Riemann condition is this. So substitute del gx by del d sigma. So take derivative of this with respect to sigma and then take derivative of this with respect to omega. You will get the same value. I would like you to verify these results. Do it yourself and then check, verify that these results are valid. Analytical in the entire S plane except at S equal to minus 1, which is called a singular point. So these singular points are called poles and zeros. So let us take a complex function gs, which is represented in terms of a ratio of polynomials in S like this. gs is bm s to the power m plus bm minus 1 s to the power m minus 1 plus bm minus 2 s to the power m minus 2. And this process goes on till b1s plus b0 divided by sn plus an minus 1 sn minus 1 plus an minus 2 sn minus 2 up to a1s plus a0. M is the order of numerator polynomial and n is the order of denominator polynomial. And a and b's are real coefficients, some of which may be 0. So by definition, the pole of the complex function gs are called the roots of the denominator polynomial, whereas zeros of the complex function are called the roots of numerator polynomials. Okay. So this is very, very, very important definition of poles and zeros. This is asked in each and every exam of control systems. Wherever you are being asked any question about control system, you are sure to be asked some of the questions on poles and zeros. So I want you to take this notes very seriously and write the definitions of poles and zeros in your notebook. Take the notes and upload it after this class is over on the Google Classroom. I will create an assignment there. So you have to upload the written material of this class. All right. So take notes. So if we take the example of this gs equal to this function k into s plus 2 into s plus 10 upon s into s plus 1, s plus 5, s plus 15 square, then we can find out the poles and zeros of this function like this. If you substitute this equal to 0, s plus 2 equal to 0, then we have a 0 at s equal to minus 2 and at s equal to minus 10. Similarly, substitute the numerator polynomial in each term equal to 0. So you get first pole at s equal to 0, second pole at s equal to minus 1, third pole at s equal to minus 5, then another pole at s equal to minus 15. And this, because it is a square term, therefore we call it as a pole of multiplicity of 2. Right? We can have multiplicity of 3, 4 or 5. So these are called complex poles of having order multiplicity more than 1. Okay, so the concepts of poles and zeros are fundamental to the analysis and design of control systems, and it simplifies the evaluation of a system's performance. Okay, so why these are called zeros? Zeros are called zeros because they are the values of the frequencies at which the transfer function of a given system becomes 0, right? Because if you substitute s equal to minus 2 here, you get 0 value, and 0 multiplied by any other value gives you a 0, right? So at s equal to minus 2, gs becomes 0. So s is a frequency at which the system's response becomes, the system's transfer function becomes 0. Therefore, this is called s equal to minus 2 and minus 10 are called zeros of the system. And why poles? Because at s equal to these values 0, minus 1, minus 5, minus 15, this the value of gs becomes infinite, right? Because 1 upon 0 is infinity. Okay, so we call 1 upon 0 as infinity and we call it as a pole, because at this frequency the transfer function, this gs is the transfer function, s is the frequency. So the frequency at which the transfer function gives infinite value, transfer function assumes infinite value, is called the pole. Okay, so these are the definitions of poles and zeros, and these are very, very, very important part of every control systems. So a complex function can also have infinite number of poles and zeros. So if a function approaches infinity as s approaches infinity, then the function has a pole at infinity, right? If the function approaches 0 as s approaches infinity, then a function has a 0 at infinity. So in our example, gs contains 3 infinite zeros. So to illustrate, let's put s approaches infinity, right? So the gs becomes, when s approaches infinity, gs becomes approximately equal to k upon s into s into s. So each s in the denominator causes gs to become 0 as s approaches infinity. Hence, gs has 3 zeros at infinity. So every function of s has an equal number of poles and zeros if we include the infinite poles and zeros as well as the finite poles and zeros. Okay, so let us do the very, very basic theorem, which is the Euler's theorem, which every student of the class must know, and that is called e to the power g theta equal to cos theta plus j sin theta. This is Euler's theorem, you all know. And furthermore, e to the power minus j theta is the complex conjugate of e to the power j theta. So e to the power minus j theta is cos theta minus j sin theta. Okay, and after adding and subtracting these two, equations, we find that cos theta is e to the power j theta plus e to the power minus j theta upon 2, and sin theta is e to the power j theta minus e to the power minus j theta upon 2j. These are the Euler's formula to relate the sinusoidal functions to complex exponential functions. I want you to note down these equations. These are very fundamental theorems, and you must be familiar also. Thinking that you have a class on Friday free? In the timetable it is showing 10 to 9, 10 to 11 class free. Class students,
Yes, ma'am.
in the timetable I am seeing here that 10 to 11 class is free on Friday. Can you
Yes,
see?
ma'am.
So you don't have a class
Yes, no, we don't have.
10 to 11. So what I was thinking that I can take your this class on tomorrow, and I have some work on Monday. So Monday I won't take your class. I will take 10 to 11 and then 11 to 12. Two classes continuous on Friday. Will it be okay with you? So Monday I won't take any class. Monday I have some work. I have to go somewhere. All right. I would try to shuffle my class, but if that doesn't happen, then I will take your this class 10 to 11. Okay, and in the continuous manner, I'll be taking why to waste this class. I will be taking this class, and maybe I will be leaving this class. 10 to 11 Friday. You can note down that I'll be taking your 10 to 11 class. Okay, I'll write on the Google Classroom also. So Laplace transformation definition is, let us take a function ft, which is a function of time such that ft is equal to 0 for t less than 0. So ft exists only for positive value of t. S is a complex variable, and L is the Laplace operator symbol, and Fs is the Laplace transform of ft. So the Laplace transform is given by Laplace transform of ft, and it is equal to Fs, and the definition is integral 0 to infinity ft e to the power minus st dt. Okay, this is the basic fundamental definition of a Laplace transform. The reverse process of finding the time function of ft from its Laplace transform Fs is called the inverse Laplace transformation. And the notation of the inverse Laplace transformation is L inverse. And the inverse Laplace transform can be found by the following integral. N inverse of Fs is ft, and it is basically 1 by 2 pi j integral c minus j infinity to c plus j infinity Fs e to the power st ds for t greater than 0, where the real constant c is the abscissa of convergence, which is chosen larger than the real parts of all singular values of Fs. So evaluating the last integral appears complex. Therefore, in practice, we seldom use the integral formula for finding ft. There are other simpler methods of finding ft. Okay, so I would like you to take down these notes. These are very fundamental theorems and very basic formula, but students don't know, and when we ask in the examination, they often don't. Yes,
Ma'am, what is unilateral and bilateral Laplace transform?
यूनिलेटरल एंड बायलेटरल, अभी तो उसकी बात ही नहीं हो रही है. अभी तो बेसिक लैप्लास ट्रांसफॉर्म की बात हो रही है.
Okay, ma'am.
अभी पहले बेसिक तो समझ लो, बताएंगे आगे, अभी आएगा.